Hello and welcome to another episode of the Prof series. In this episode we'll cover the researcher Dr. Max Jones. Dr. Max Jones teaches part of the biology of managed ecosystems at the University of Guelph. He is a specialist at tissue culture and breadfruit. For this episode we'll be talking about his work in Echinacea. Let's get started. Echinacea is a traditional medical herb used historically throughout many parts of the world within the Americas. First by several indigenous tribes within this region, and later on by European explorers who either obtained this knowledge or independently discovered it. There's a high variability within the gene pool, especially when it comes to the variability between medically important compounds within Echinacea. One of the most important ingredients within Echinacea is caicoric acid, and the concentrations can range between 1.4 and 20.5 milligrams per gram. To that end, the propagation of specific individuals that have the compounds required will reduce the variability by considerable margin. However, to do so effectively, one needs to tissue culture this plant quite rapidly to make it economically viable. To that end, there's great interest in improving this process of tissue culturing Echinacea using different chemical compounds, such as auxins. These auxin-mimicking chemicals can create somatic embryos, shoots, roots, and plantlets that can be utilized to produce new plants. 2,4-D, TDZ, and dicamba are candidates for this process. To that end, two systems were used. A solid system, in which a solid medium was used for tissue culture, and liquid medium, also used for tissue culture, was set up. In one group, the solid medium is supplemented with TDZ, in another group is supplemented with 2,4-D, and in a third group is supplemented by dicamba. All groups were supplemented with different concentrations of these chemicals, ranging from 0.1, 0.5, 1, 2.5, 5, 7.5, and 10 micromoles of different compounds. Now here are the results. TDZ above 0.1 micromoles induce significantly higher growth rates than dicamba or 2,4-D. The cultures developed a combination of callus tissue and regenerating structures, while dicamba and 2,4-D only produce callus tissue, but nothing else. The plants regenerated from TDZ-induced callus tissue were of two types: artificially generated embryos that were identical to the mother parent. The other tissue that was formed was elongated shoots. Both the generation of these shoots and artificial embryos have been documented in other papers. All the resulting plants had visible primordial leaf or cotyledons, depending if it was a shoot generated or an embryo generated, respectively. The amount of plants that appeared increased with concentration with TDZ. 2,4-D and dicamba only form callus and roots, but not shoots or somatic embryos. Despite that, some other groups have found that 2,4-D did form embryos, although this occurred with the use of different tissues, specifically hypocotyls rather than leaf tissue. In previous experiments, combinations of 2,4-D along with a cytokinin compound in all cases can produce somatic embryos, but TDZ can take the place of both an auxin compound and a cytokinin compound. The results are similar to what's found in other species, one such example being African violets. So this is how it went down within solid culture medium. The same results were found in liquid medium, however the amount of plantlets, whether it be shoots or somatic embryos formed, maxed out between 0.1 micromoles and 1.0 micromoles of TDZ. Higher rates of plant regeneration occurred better within a solid medium, as within the solid medium, rates of plantlet formation increased with increasing concentrations of TDZ. In both systems, the survivability of these embryos ranged between 89% and 96%. After these were grown and hardened off, both the plantlets and somatic embryo-derived plants could be grown to fully grown, conventionally grown Echinacea plants. Dr. Jones concludes that this method could improve the viability of mass-producing Echinacea cultivars for future use. And that about covers everything. Thank you for watching this video. If you enjoyed this video, please like and subscribe. If you really enjoyed it and think you can donate, you can do so at Buy Me a Coffee, link in the description below. Thank you for watching.